It gives me great pleasure now to introduce Yasuko Takei, another one of the co-organisers of the Melt in the Mantle program, and she's going to talk now about the effect of partial melting on the seismic velocity.
Thank you. I am Yasuko Takei from ERI University of Tokyo. I am collaborating with my student Yamauchi-san, and also I collaborated with Christine McCarthy now in Vermont. First, I talk about introduction. Recently, we can obtain a highly resolved image of volcanic source regions by seismic tomographic study. This slide shows the shear wave velocity structure beneath the Pacific Ridge obtained by Priestley and Mackenzie, and beneath a subduction zone in Japan obtained by Nakajima et al. The low velocity regions, these red regions beneath volcano, are considered to be related to the partial melting of rock. So, using these structures, we want to explore the partially molten region to know how large it is, how much melt exists, and what temperature it is, etc. But it is still difficult to answer these questions because we have a fundamental difficulty that we do not know well about the high temperature property of rock. So I first talk about this difficulty as an introduction of my talk. This figure shows the shear wave velocity of peridotite measured in the laboratory as a function of temperature. This data was obtained by Isaac in 1992 and has long been used in the interpretation of seismic data. If shear wave velocity below this line is obtained in the volcanic source region, until recently, we simply considered that the low velocity is caused by melt. So if we obtain this data, this difference, 5%, was explained by melt. And to calculate the effect of melt, partially molten rock was modeled by a solid liquid composite system in which melt is treated as inclusions contained in a continuum solid phase. The elastic property of this model can be calculated by the poroelasticity theory. Because the result is sensitive to the assumed shape of the inclusions, we have to consider the realistic shape of melt observed in the laboratory. The effect of melt calculated by this theory can be simply stated that the fractional change in shear wave velocity by melt is about twice the melt fraction. So, the 5% velocity reduction means that the melt fraction in this region is 2.5%. And this way of thinking was commonly used until recently. However, in 2002, Jackson et al. Published their data shown here by these red lines. Although they used melt-free peridotite, their data at high temperature was much lower than the previous data by Isaac. So if we use these new data, this example just now can be explained without invoking melt. So this difference is significant, and you may be wondering why these two data sets are so different. And the difference between these two studies, two experiments, is in the testing frequency. Isaac tested the sample at about 1 megahertz, but Jackson et al. Tested at much lower frequencies, like 0.33 hertz and 0.01 hertz, which corresponds to the seismic frequencies. And these are the experimental settings. ISAC used a free oscillation of a small peridotite sample at about ultrasonic frequencies. In contrast, Jackson et al. Used a forced oscillation test. A cylindrical sample of peridotite was deformed in torsion slowly from 1 hertz to 1 millihertz. So, this difference means that rock is stiff when deformed quickly, but soft when deformed slowly. And such frequency dependence of the elastic response is called dispersion, and the material property responsible for the dispersion is called anelasticity, or unelastic relaxation. And one of the most important sources of rock anelasticity is a slip at grain boundary. Grain boundary is weaker than grain inside, and so if temperature is high enough and the deformation is slow enough, grain boundary cannot sustain the applied shear stress and slip a bit, causing a further deformation of the aggregate. So, since the importance of rock anelasticity was demonstrated by Jackson et al., this simple model has been modified to include the grain boundaries as slip planes. So, in addition to the poroelasticity, we have to understand the kinetics of the grain boundary. And this is a major concern of my talk. Because the laboratory samples usually have very small grain sizes like this, to avoid the thermal cracking between heating and cooling. So, in the application to the mantle, extrapolation of the grain boundary from a few micrometer to a few millimeter is necessary. So, in order to use the Jackson's data correctly, we have to know the scaling law for the anelasticity. And this is a key question of this problem. And in this talk, I will give an answer obtained from our experimental studies and apply it to the mantle. Okay, in the first topic, I introduced modulus dispersion observed in the mantle rock. And next, before talking about experiments, I will briefly talk about the relationship between dispersion and attenuation. Because of rock anelasticity, shear wave velocity of rock decreases with decreasing frequency. Attenuation is also caused by anelasticity. So, velocity dispersion and attenuation are both caused by anelasticity and are mutually related to each other. And under some reasonable assumption, this relationship can be simply stated that the slope of velocity is equal to the attenuation at this frequency, and which can be explicitly written like this. And this relationship can be more conveniently stated that the amount of velocity reduction at this frequency is equal to the integral of attenuation above this frequency. So, if this is too dilute, but if this is seismic frequency, this means that the seismic wave velocity is influenced by all attenuation which exists at higher frequencies than this frequency. So experimental studies are focusing on the understanding of attenuation. Now I will talk about experimental studies. Experimental studies of rock anelasticity have been performed intensively by Jackson's group in ANU by using melt-free olivine aggregate and melt-bearing olivine plus basalt system. However, because of the difficulty of high temperature experiments, data are limited and are not enough to clarify the scaling law. So we are measuring anelasticity by using analog material. Polycrystalline aggregates of organic borneol is used as rock analog, and binary eutectic system of borneol plus diphenylamine is used as partially molten rock analog. This is a phase diagram of borneol plus diphenylamine. Melting temperature of borneol is 204 degrees C. But when the secondary component, diphenylamine, is mixed, the mixture partially melts at 43 degrees C and becomes a very good analog of partially molten rock. The dihedral angle is 35 degrees, and the equilibrium geometry of melt is quite similar to the partially molten rock. And in this system, melt fraction can be controlled accurately by changing the amount of diphenylamine. Anelasticity is measured by the forced oscillation test. Jackson's group is measuring shear attenuation and shear modulus and shear attenuation by using torsion test. In contrast, we are measuring Young's modulus and its attenuation by using uniaxial compression test. However, because of a large Poisson's ratio of borneol, dispersion and attenuation of the Young's modulus are mostly determined by the shear component. So our data can be directly compared with their data. And here, run temperatures of each samples are shown along the axis of homologous temperature normalized to the melting temperature or solidus of each sample. By using the analog material, high temperature property corresponding to 900 to 1200 degrees C of mantle rock can be measured near the room temperature. And at the same run temperature, binary system has higher homologous temperature than the pure system because the secondary component significantly decreases the solidus temperature. Typical attenuation spectra are shown here for these samples as functions of period, and the color shows temperature. So attenuation spectra are similar between olivine and borneol, and between olivine plus basalt and borneol plus diphenylamine. So we consider that the underlying physics have something in common. And the frequency range is 3 orders of magnitude in the rock samples, rock data, but our data has 6 orders of magnitude, which is favorable to investigate the scaling law. Okay, now I will talk about the scaling law for anelasticity obtained from our studies. One of the most important scaling law for anelasticity is the Maxwell frequency scaling. The Maxwell frequency is defined by the unrelaxed Young's modulus divided by viscosity of the diffusion creep. And this is a characteristic frequency of viscoelastic material below which viscous deformation becomes dominant. This figure shows our previous data obtained with Christine for various temperatures, grain sizes, chemical compositions, and melt fractions. And when the testing frequency is normalized to the Maxwell frequency of each sample, all attenuation spectra obtained under various experimental conditions collapse onto a nearly single master curve. And with this scaling, data from olivine aggregates collapse onto the same master curve as Borneol. This result can be understood by the physical model of grain boundary sliding. The grain boundary sliding occurs to relax the tangential stress at grain boundary, but there are a lot of obstacles to the sliding, like grain edges and grain boundary steps at atomic scales. So the grain boundary sliding is considered to occur by the following two stages. First, before being stopped by the obstacles, sliding occurs locally along the planar segments between the obstacles. And this stage is called elastically accommodated grain boundary sliding. After being stopped by the obstacles, sliding occurs slowly and globally by overcoming the obstacles by matter diffusion. And this latter stage is called diffusionally accommodated grain boundary sliding. The rate limiting process of this latter process is matter diffusion, and the viscosity of the diffusion creep is also rate limited by matter diffusion. So the reference frequency of this latter process can be given by the Maxwell frequency. And so the efficiency of the Maxwell frequency scaling observed in our experimental studies can be explained well by the diffusionally accommodated grain boundary sliding. So now the attenuation spectra can be given by a master curve, which is a function of single master variable f over fn. And this result was supported by experimentally and theoretically. So I first thought that this problem can be solved completely. However, when the seismic frequency normalized to the Maxwell frequency in the mantle is plotted, it becomes considerably higher than the experimental data. So the question remained whether the Maxwell frequency scaling is applicable to the seismic range or not. But at this stage, we optimistically assumed this question yes, and proposed a master curve model. And because we did not have any data points here, we just assumed this shape. And after the publication of this master curve model, in order to answer this fundamental question, we improved our experimental method and obtained the data at higher normalized frequencies. And these new data, published in 2014, clearly show that when normalized frequency is high, attenuation varies significantly depending on each experimental condition. And so the behavior at high normalized frequency cannot be fully captured by the Maxwell frequency scaling, and so the answer to this question is no. And for the seismological application, we have to clarify the rule of this variation. So, for a detailed look at the variation, we introduced the background dissipation like this and represented each spectrum by the superposition of the background and the deviation from the background. And the deviation is called peak because it has a shape of broad peak. In this figure, color shows temperature, and the symbol size shows grain size. Open symbols show pure samples, and solid symbols show binary samples. The homologous temperature is higher for the binary samples. So, the variation is quite systematic. As shown by these pink arrows, the center frequency normalized to the Maxwell frequency is constant for all data, and the amplitude and width of the peak increase with increasing homologous temperature and increasing grain size. So we understood that the background dissipation follows the Maxwell frequency scaling, but the peak dissipation does not fully follow because of a systematic growth of the peak with increasing homologous temperature and increasing grain size. In the seismic range, background is very small and peak becomes dominant. The data from olivine aggregate are also divided into the monotonic background and the broad peak. So our data are basically consistent. However, in the olivine data, it is difficult to investigate the detailed behavior of peak because of a narrow range of frequency and a lack of good viscosity data to calculate the Maxwell frequency. So, this systematic behavior of peak was newly recognized in our study. And the highest homologous temperature of this data set is 0.93, which is lower than the solidus temperature. However, the peak is already broad and large, so this suggests that the seismic low velocity and high attenuation can occur below the solidus even without melt. And we consider this suggestion very important, and to apply our data to the mantle, we performed a parameterization of our result. And here, the normalized frequency is written as f dash, and homologous temperature is T dash. And as shown here, background dissipation is given as a function of f dash, and peak dissipation is given as a function of f dash, T dash, and grain size. And background is a power of f dash with constant amplitude and constant exponent. And peak is a Gaussian with constant peak frequency and variable peak amplitude and variable peak width. So to complete this parameterization, we have to determine the form of peak amplitude and peak width as functions of homologous temperature and grain size. However, this data set is limited to the subsolidus temperature and does not include the behavior at partial melting, which is important in the upper mantle. So we obtained a new data set which covers a wider range of temperature from below to above the solidus temperature. And this figure shows a typical result of anelasticity and viscosity. The left figure shows Young's modulus and attenuation as a function of frequency, and the color shows temperature from 0.88 to 1.01 homologous temperature at almost regular intervals. So, as temperature increases, Young's modulus decreases and attenuation increases continuously. And these open triangles show the partially molten data with 0.4% melt fraction. And these horizontal lines show the unrelaxed Young's modulus measured by the ultrasonic waves in the same color scheme. So, this deficit at 100 Hz is equal to the integral of attenuation existing above 100 Hz. So, for each spectrum, although the detailed shape above 100 Hz is unknown, the integral above 100 Hz is known from the modulus data. And this information can be used to constrain the total relaxation strength of the peak dissipation even without any data points above 100 Hz. And right figure shows viscosity as a function of inverse absolute temperature, showing that the viscosity decreases as temperature increases. And using these measured viscosity and unrelaxed Young's modulus, we calculated the Maxwell frequency for each temperature and normalized the frequency of this figure by the Maxwell frequency. And this, as before, this result is represented by the superposition of the background and the peak. And by fitting the parameterized models to these data, we determined the peak amplitude and peak width, as a function of homologous temperature. Although the result of only one sample is shown here, similar curves were obtained robustly regardless of grain size and chemical composition. The grain size dependence was observed in the previous data set, but was not in this data set. The grain size was from 4 to 20 in the previous data set, but from 20 to 50 in this data set. So we considered that the grain size effect on these parameters were saturated and neglect it for simplicity. So we use these curves as universal growth curve of peak dissipation near the solidus temperature. Okay, here our anelasticity models are summarized, and the essential difference of the new model from the previous master curve model is the change of the spectrum shape by temperature. Also, in the previous model, this high frequency part was just assumption, but in the new model is more faithful to the experimental data. The important consequences of these differences will be shown in the application, but before talking about application, I briefly discussed the underlying physics of this new model. And here, systematic change of attenuation spectrum by homologous temperature is summarized from subsolidus, near but below solidus, and to supersolidus temperatures. At about 0.95 homologous temperature, the peak dissipation is broadened. And at this temperature, viscosity also showed a remarkable behavior. In this previous slide, we can see a bend here at 0.94 homologous temperature, showing that the reduction of viscosity by temperature was accelerated at this homologous temperature, and this behavior was observed robustly. So what is the cause of these changes below the solidus temperature? You may think that partial melting started below the solidus temperature, but if we look at the microstructure annealed at 0.99 homologous temperature, diphenylamine exists as isolated grains, and we cannot see any sign of partial melting. In contrast, in the microstructure annealed at 1.01 homologous temperature, a connected network of melt exists at triple junctions. So these changes at 0.95 are caused by the solid state mechanism. And because the peak center follows the Maxwell frequency scaling, diffusionally accommodated grain boundary sliding may be playing an important role. So we consider that the dynamic state of grain boundary changes at this homologous temperature. And a transition of grain boundary structure below the bulk melting temperature is known as pre-melting. And we speculate that a similar phenomenon to pre-melting occurs below the solidus temperature. But this is just speculation. The last topic is the application of the anelasticity model to seismic data. Shear wave velocity structure of Pacific mantle was obtained by Priestley and McKenzie 2013. And the thermal structure in the upper 100 kilometers of the oceanic mantle was calculated by McKenzie et al. 2005 by using the plate cooling model. These two results are shown here by the profiles in the horizontal direction obtained at 50 and 75 kilometer depths. The upper figure shows temperature profiles and the lower figure shows velocity profiles, both of which vary slowly, extending over more than 15,000 kilometers away from the ridge. And when the solidus temperature at these depths is plotted in the same color scheme, we can see that all the data are below the solidus temperature. And the first data point is about 100 kilometers away from the ridge center. So the lateral scale of the partially molten zone beneath the ridge is considered to be smaller than this first data point. So the behavior of these data is a subsolidus behavior. by combining these two profiles, they obtained a temperature dependence of the shear wave velocity, which shows a steep decrease just below the solidus temperature. And this curve is similar to the laboratory data which I showed in the introduction. And in this data, this linear part shows unrelaxed velocity determined by the intrinsic elasticity of the mineral, which is relatively known. And the further reduction at high temperature shows an elastic effect, which is unknown and our present concern. And as they stated, their data is a mantle version of this curve and provides a valuable opportunity to test the applicability of the elasticity models obtained in the experimental studies. So our models were tested by these data. The master curve model, which was published in 2011, was already tested by Priestley and Mackenzie. So during my stay in Cambridge in this melting mantle program, I tested the new model by using the method and the program developed by Mackenzie. So I will show the results of these tests, which clarify the seismological implication of the new model. The testing procedure can be summarized as follows. When the attenuation spectrum is given by these models, by using the relationship between dispersion and attenuation, the shear wave velocity at frequency f can be calculated by this equation, which includes wave frequency, unrelaxed velocity, and Maxwell frequency. In this application, wave frequency is fixed to 0.01 Hz, and the other two quantities are calculated by the density, elasticity, and viscosity of the peridotite. Although these material properties are available from the seismological data, there exist some uncertainties. And in their analysis, these 6 material parameters representing elasticity and viscosity and their temperature, pressure dependencies were obtained as fitting parameters when the resultant velocities are fitted to the seismic data. So the applicability of the model is tested by how close the fit to seismic data is and how reasonable the obtained fitting parameters are compared to the laboratory data. And in the fitting, some other data were also used as geophysical constraints, but the result is not so sensitive to these data, and so only the fitting to this data is shown here. And this is the fitting of the master curve model. And this is the fitting by the new model. The new model can explain well the steep decrease just below the solidus temperature. In contrast, the velocity reduction by the master curve model is small and not steep. And this discrete reduction is not the solid state effect, but due to the large reduction of viscosity by melt, which was assumed in the previous their analysis. So when we remove this part and plot only the solid state effect, we can see the difference between the two models clearer. In the master curve model, anelastic effect starts at about 1000 degrees C, which corresponds to 0.77 homologous temperature. But in the new model, it starts near the solidus, corresponding to 0.94 homologous temperature. So in the new model, anelastic effect and partial melting is closely related. And this result can be explained by the attenuation spectrum. The vertical lines shown in the master curve model show the normalized frequencies at 50 kilometer depth and at several temperatures shown by the same color. Although frequency is fixed to 0.01 Hz, the Maxwell frequency changes with temperature because viscosity changes with temperature. So as temperature increases, the normalized frequency decreases like this, and the amount of velocity reduction by anelasticity is calculated by the integral of attenuation above this line. So as temperature increases, this integral increases from this blue area, green area, orange area, red area, like this. And the velocity reduction by the new model can be also calculated in the same manner. But in this case, in addition to the normalized frequency, the spectrum shape changes with temperature. So this integral is 0 for blue curves and 0 for green curves and this small area for orange and this big area for red. So the anelastic effect increases very steeply with temperature. And the position of the normalized frequency relative to the spectrum is, and also the movement with temperature are determined by the viscosity and the activation energy of the viscosity. So these two parameters are well constrained by this fitting. And here the obtained fitting parameters are summarized. And viscosity and activation energy agree well with the experimental data obtained for olivine aggregates. And other parameters are also reasonable. And particularly, the agreement of this unharmonicity parameter was increased by the new model. So we consider that these results suggest the applicability of the new model to the mantle. So by assuming the applicability, I summarized the conclusions and the implications. Anelasticity at high normalized frequency is enhanced from below the solidus temperature in the absence of melt. As a result, anelastic effect on the seismic wave is closely related to the partial melting. Also, larger region than the actual partially molten zone is detected as seismic low velocity and high attenuation zone. Also, when melt fraction is very small, the anelastic effect dominates the direct effect of melt, which becomes very small for small melt fraction. As a result, seismic low velocity and high attenuation can occur even if melt fraction is very small. That's all. Thank you very much.
Thank you very much. Questions?
Yeah, very nice presentation. Yeah. And, a few questions. When you say Maxwell frequency, to me this is a very vague concept because Maxwell frequency is the frequency ratio between viscosity and elastic constant. Elastic constant is well defined, but viscosity depends on various
Mechanism?
Yeah. So
Yes. For the this is theoretical support comes from the diffusionally accommodated grain boundary sliding. The
yeah, that's a theory.
Yeah, so
when you say
So the good relationship to Maxwell frequency can be obtained when viscosity is diffusion creep viscosity. So if viscosity is dislocation creep, then the elementary process is different from the.
So you also explain the high frequency broad peak by
diffusion, matter diffusion, and also viscosity should be rate limited by diffusion. The same elementary process. So in this context, in anelasticity context, viscosity should be diffusion creep viscosity.
Okay.
And if it the yes, so yes.
And how, so you have a new model at high F over Fm domain. How does your model prediction of frequency dependence agree with the seismic?
Frequency dependence is not affected by this change. The temperature dependence is significantly affected by, but the frequency dependence at constant temperature is not so different from the previous.
Because in your new model, seismic frequency range is in certain areas, right? If you have a peak, and then frequency dependence could be either positive or negative.
Frequency dependence is determined by this.
Yeah.
So for constant temperature, frequency dependence is given by this line. So in this sense, previous concept understanding in seismology, this curve is always same shape, and frequency dependence. My answer is enough. Frequency dependence is
your
the
model
same.
explains like a seismologically inferred frequency dependence, like 0.3.
I come in on this. The velocity that Yasuko is using is from surface wave tomography in a period range from 50 to 160 seconds.
Okay. So
right, which we assumed, right, when we did that stuff, is for these purposes is constant, and that's the frequency that we're using.
We're
not. This isn't the short period.
Yeah, I was not asking particular work, but I was curious if your model explained the seismic data from much broader frequency range.
So I only applied to the surface wave data. So, but very different part of this model does not so affect to the leakage dependence. The temperature dependence is very significantly changed by the.
Sorry, slightly different thing. Did I understand your experimental results to say that the attenuation actually increases with grain size as well? Do you understand what that effect is?
I think yes. Grain size determines the Maxwell frequency. Maxwell frequency becomes very low, and I think the first shortest time scale will be determined by smallest obstacle, like atomic scale or something. That is maybe the shortest time scale, and the longest time scale is Maxwell frequency. So the grain size is large. The shortest and the largest time scale is very different, but the grain size is small. Shortest scale and the largest scale is similar, and this broadening of peak by increasing frequency, I think it's because of the broadening of spectrum occurs because of that wide range of time scale.
So,
yeah, by the
if I understand.
space.
So you're saying that effect, the absolute attenuation, does it actually increase with grain size, or is this shift due to the scaling with the Maxwell frequency?
Absolutely.
Do larger grains, are they more attenuated or
Yeah, the data shows that.
Yes, so the Priestley and McKenzie work is a large-scale model, and so it resolves hundreds of kilometers. But if we have ocean bottom seismographs, we get a more detailed picture of the velocity structure near the spreading centers, and then we get velocities of about 3.8 or 3.9, and so, and then we get attenuation, S wave Q of like 40 or 30. So how would your model explain that kind of data? So you would have some small amount of partial melt?
At least the 3.9 is so far difficult without relatively large amount of melt. Do you think the melt fraction is relatively large at that point? Do you know the melt fraction?
We don't
So larger than.
I think there's quite a bit of evidence from the other kind of work that goes on that the melt fraction should be relatively small.
Okay.
But
yeah.
less than 2% or something. But
in this analysis to the Priestley and Mackenzie's data, I did not include any melt effect or a subsolidus effect. I just put, and if there is melt, we can add some poroelastic effect, and also we see that if melt fraction, our largest melt fraction sample was 1.6% melt fraction, and in that case, peak after melting occurs, some peak amplitude increased by melting. So if there is some not small melt fraction, then we can add some more anelastic effect and direct effect, poroelastic effect, and that can be the source of further lowering of the velocity. But if melt fraction is much smaller than 1%, our subsolidus model cannot explain 3.9 kilometer per sec. So without melt, such small low velocity, so low velocity is still difficult. Seems to be difficult at this stage.
Right.
Yes.
The near-solidus behavior is very interesting, and then one of the key points is alright. So
Yeah.
that's explained.
Mm.
But if you look at the microscopic basis, you invoked something like pre-melting.
No,
No?
we do not need we do not need melt. We consider the grain boundary transition.
Yeah, such a pre-melting.
Pre-melting is not a melting, but a solid state, completely solid state.
My
melting.
question is, the pre-melting has been demonstrated by several people, including my colleagues.
Your colleague.
Yeah, my
Okay.
question is, as far as I understand it, pre-melting is very sensitive to impurities.
Haha.
And then I'm wondering if material properties are so sensitive to impurities, to what extent, I'm wondering to what extent the choice of analog material
Mhm.
can be justified.
Yeah, at least at this experiment, it occurred just below the solidus temperature of the binary system. Of course, I think this material has many other impurities, but the peak dissipation behavior of peak dissipation had a good correlation with the solidus temperature predicted from the Borneo and the diagonal amine binary system. So I am feeling that this phenomena can be predicted for the binary system, but I don't know, maybe it can be. So something else is affecting. That is, of course, possible.
Garrett, can you remind us where when you plotted the seismic velocities versus temperature, where did the temperatures come from? And presumably they're independent from the seismic observation? This is from the
This one.
Mackenzie. Yeah, right.
What is your
Are those temperatures from where are the temperatures from? And this,
temperature was Mackenzie's.
was that inferred from? Is that just a thermal model, or?
Yes.
Yes.
Okay, so you know those temperature. So there's no independent. What are the constraints on the temperature? What are the constraints on the temperatures?
Sorry, you should answer. Sorry about that.
Sorry, I have not yet understand the question.
Where
gonna
the
fit a
greatest
model.
temperature comes from. I mean, it's a plate model. Fit. I mean, Dan could explain. Dan,
Sorry.
I mean, it's a model which was developed for a different purpose, which was to account for the depth versus age and heat flow versus age. The points on it, right, are the depths of the earthquakes, right, in the ocean. So for our purposes, you can ignore the points, but the temperature, the temperature structure. What is important is that the thermal conductivity varies with temperature by about a factor of 2. And you can see that with the spacing of the contours between the top and the bottom. So this was a model which was devised for 2005 for rather different purposes. And what I did was to take various estimates from go back a bit. The problem with taking any laboratory measurements of attenuation and velocity and applying it to the mantle is that they're grain size dependent. So what I decided to do instead was to take all the estimates we had of temperature and velocity from spreading ridges, from nodules in continental regions, and from the isentropic temperature, the average temperature beneath the Pacific. I wanted to make 7 kilometers of melt when you decompress, because that's the thickness of the oceanic crust. And then saw whether I could, by adjusting the parameters in Yasuko's model, whether I could then get her model to actually fit the data. Right. Now, the one thing which hasn't come out in this discussion so far, which is very relevant to your question, which is that the velocities are from surface wave tomography. Right? So they have limited spatial resolution. And the question, so in the parameterization, which Yasuko showed, there is an impact of the actual resolution of the tomography in there. Right? And that's why when we don't see, because the tomography doesn't see it, velocities as low as 3.8. But since you have all these adjustable parameters, there's actually no difficulty in fitting velocities of 3.8. But as Fermi famously said, right, with 4 parameters I can build an elephant, with 5 I can get it to wag its tail. So you need to be careful. I mean, the proof of the whole thing is really that the parameters are coming out in the right sort of region of what we know from rather independent things. As Yasuko showed, could you put up the one of the parameters again?
Table, yeah.
The table, yeah. Because I think this is important. That when we did all this, right, you compare the ones on laboratory alternative data with those from the modelling, you can see that particularly the elasticity, the anharmonic effects, and all of that is in the right ballpark. The activation energy in the laboratory data, that's for creep. And you can see that there's quite a range from people like Dave Colstead's estimates. The log eta 0, that gives you a grain size of somewhere around a few millimeters using their parameterization for the viscosity. So there's no obvious problem. But to cause these things to match 3.8 kilometers per second rather than 4.1 is no problem at all. With this many parameters you can do it. So all I could, this side of it was really governed by seeing whether there was any obvious problem between the observations, right, and what Yasuko had done in terms of the parameterization. And I think the answer is no, there isn't. Right. But the details of it are changing all the time, because Keith has just on the Friday before this meeting started, he gave me a new tomography model which now uses 5 million seismograms, right?
I guess the main thing is Yasuko was showing lines for solidi that mismatched where the data were by tens of degrees. So do we know where the solidi is to 10 degrees? And are those temperatures clearly independent? Well, it's clear. It's important that those temperatures are independent from any seismic velocity, right? So as long as your thermal model is independent from any seismic velocity,
you put together two things, right? One is that the curves for the temperatures, right? The velocity temperature curves from the ridges, there the temperatures are completely independent of the velocity.
right?
Where Yasuko put the solidus temperatures are not independent of the velocities, because that was one of the bits of the parameterization. Right? If you go on, I think.
Next one.
Yeah. Now, those temperatures, I'm not quite sure where you got those temperatures from, but those from the parameterization.
This temperature.
Yeah.
This was your subroutine. That is dry solidus
Right.
of period.
Oh, those are the straight dry solids.
Yeah, but after the fitting,
Yeah, after the fitting.
after the fitting was
Yeah. Stick those on.
this one.
Now, those
Yeah, this,
are adjusted to fit the curves.
yeah.
So you've
this
got a
is
mixture
dry.
of two things. The ones on the right are from laboratory experiments on melting, right? So they are essentially prototype melting experiments, right, from a whole variety of sources, right, which essentially Mark Hirschman's, right. The ones on the left, the lower left one, those are from trying to adjust the solidus temperature to match Yasuko's new curves, right? So you've got two things in there.
But at 75 kilometers, you're just about, and typical potential temperatures, you're just about at or below the dry solidus anyway. So the fact that the solidus is lowered by 75 degrees may have to do with volatiles.
Yep, in the lithosphere.
So the fact that it doesn't match 1436, to me, it doesn't raise any red flags. You wouldn't expect to have a perfectly dry mantle anyway.
I completely agree. I mean, the question is whether there's any obvious trouble, and I can't see that these show that there's obvious trouble. I mean, but now you've got 9 parameters. So you've got 2 others to look at.
Is it possible that your temperature model is influenced by the real temperature near ridges that are reduced due to latent heat of melting?
Now that's in there. That's in there. The model temperatures there take account of the decompression melting and the reduction of the temperature due to the decompression melting, and that decompression melting makes 7 kilometers of oceanic crust. That's all from 10 years ago. That's all in there.
Just returning on frequency dependence of you have a wave velocity and attenuation. You increase, and there is also a grain size effect hidden somewhere. So if you increase frequency, you decrease wavelength. Is there anything special happening when wavelength becomes of the order of the grain size, or it is beyond your range of frequencies which you apply?
No, even in the ultrasonic experiment, the wavelength is larger than the grain size.
Still large.
So the
Right, you
post
don't
oscillation phase
increase
is
frequency that far, right?
almost static.
You showed the viscosity measured from experiments versus homologous temperature. So two things. You said that that small change is robust, and I just wondered if you could explain why it's robust, and also why is it that when you cross the solidus, the slope doesn't change at all?
Doesn't, yeah. So that's first of all, this means that the activation energy increases at this homologous temperature near the solidus, and this was observed robustly for various samples always. That is robust, and also nothing happened that partially more. That is also a remarkable result of our study. No jump, no sudden change. Very continuous.
So the ratio of P wave velocity to shear wave velocity is often used as a site evidence for melt. Can you speculate how
Yes,
that might be?
this anelasticity is grain boundary sliding, we consider, so affect shear modulus but not bulk modulus. So this effect is again very strongly affect to shear wave but not so to P wave. So
So a high BPBS ratio
high BPBS.
might be
If we
not
assume equilibrium shape of melt for melt geometry, the VPVS ratio is not so. The high VPVS ratio is only for thin melt shape, and for equilibrium shape, VS perturbation over VP perturbation is about 1.5 or something. But in this grain boundary sliding, VS perturbation over VP perturbation will be more than 2, I guess, because the grain boundary phenomena, it cannot be affect bulk attenuation. So maybe even higher VPVS is expected for this mechanism.
Any further questions? Oh, sorry.
So, one of the things that is interesting about the velocities in the oceanic upper mantle, and the surface waves won't see this, is the sharp change, this kind of high velocity lid with low velocities right below it, right? People talk about it as being the sphere boundary. And I was just wondering whether, if you've thought about whether the sharpness of that break does imply that you have to have melt there. And I understand that in the surface wave models, you obviously won't, that will all be smeared out. But so I was just wondering if you thought about how it applied to both spheres being surrounded.
Yeah, should be tested, the discontinuity. Yeah, have not yet.
Any last questions? In which case, can we please thank Yasuko once again?